All right, class, so this is on what happens if you have constant acceleration. So it's very rarely true that you actually have constant acceleration, but it's often true that your acceleration is close enough to being constant that you can use that model without losing too much in the way of relevant information. So we're going to go ahead and see what happens here. Okay, so hopefully you all remember that acceleration is defined as the derivative of velocity with respect to time. And that means, well, we're taking the derivative of velocity to get acceleration. So if we want velocity from acceleration, we're going to do the opposite of derivative, which is an antiderivative or an integral. So if acceleration is constant, we can go ahead and do this integral. And remember, this is the same as multiplying by 1, and anything to the 0th power is equal to 1, including t to the 0. And so here we can have acceleration, which is a constant, by definition of what we're looking at here. T to the add 1 to the power, because we're doing an integral, divide by that new power, and then add an unknown constant, which we'll call C1. And remember, we need to do that because in a derivative, if you have a constant and you take the derivative, you're going to get 0. And so when we undo the derivative for the integral, we have to assume that the fact we don't have a constant here may mean that one of those constants may have disappeared when we did essentially the derivative that resulted here. So we have to add it back in. So that means we get velocity is equal to acceleration, which is a constant number, t to the 0 plus 1, so that is just t to the first power, or just t, divided by 1 plus 0, or just 1, so t divided by 1 is t, so that's acceleration times time, plus this unknown constant. And I'm going to remind us all that velocity is a variable. It's something that varies as time goes on. So I'm going to put in parentheses this little t just to remind ourselves that v depends on the value of t. So what happens if we plug in t equals 0? That is, what's going on initially when we start the clock, when time is equal to 0? Well, we put in t is equal to 0, so this actually isn't a variable anymore. We picked one particular time, so you only have one velocity at a given time. So let's go ahead and rename that. Let's call that v naught, or v0, meaning this is the initial velocity. The velocity we have when time is equal to 0. And then a, well, that's a constant, nothing happens there, but t, we need to plug in 0, so we multiply a by 0, and then add our unknown constant c1. But a by 0, or anything times 0, well, that is equal to 0, so this whole term disappears and becomes 0. So that leaves us with our unknown constant is actually the initial velocity. And that'll happen a lot in this class. Doesn't always happen, but often this unknown constant is related to what's going on at time 0. And that happens because every other term has time in it. So when you plug in t equals 0, those terms disappear. So that gives us the velocity is equal to the acceleration multiplied by the time plus the initial velocity. So whenever acceleration is constant, we can use this equation. And this makes sense, right? Because it's the velocity you start with plus acceleration, which is the change in velocity as time goes on, multiplied by how long you've waited. So this is the change in velocity times times. This is going to be the change in the velocity total at some given time t plus whatever you started with. That'll give you the velocity you've got now. So that is an important equation. We'll go ahead and write it down permanently on this sheet of paper over here. v, which is a function of t, is acceleration multiplied by time plus the initial velocity. We'll write in sort of our notes. This is constant acceleration. It's only true when acceleration is constant. This guy is initial velocity. What else can we learn? Well, we know something about the velocity now. What about the position? We know that the velocity is equal to the derivative of position with respect to time. And so that means that position is equal to the integral over time of velocity. So again, these two are just opposites. So we take the derivative of position to get velocity. We take the integral of velocity to get position. But we have an equation for velocity. So let's go ahead and plug that in and take its integral. Acceleration times time plus the initial velocity. And normally this might be changing, so this integral would be tricky to do because it'd have some variation with t here and some in acceleration, but we've explicitly said it's constant, so that's a constant, and that's a constant. That's the velocity at one particular time, t equals 0, so we can go ahead and do this integral. Right, so we have our constant. This is just t, that's got an implied power of 1, so we would do raise the exponent by 1, 1 plus 1, divide by that new power, 1 plus 1, plus v naught's a constant. When we do the integral, that is the initial velocity v naught, multiplied by time, plus a new unknown constant, because again, we're doing the integral. We'll always get an unknown constant whenever we do an integral with undefined limits like this. So let's make this a little bit neater. So 1 over 1 plus 1, that's 1/2. We'll move that out front. So that's just this part out front. Times a, t to the 1 plus 1, that's t squared, plus v naught times t plus our unknown constant. And we'll do the same thing again. We'll plug in t equals 0. So when we do that, we're not looking at just any old x, we're looking at the position you've got when time is 0. So we'll go ahead and give that a new symbol because it's now a constant, just a plain old number. So that's initial position. And that is equal to 1/2 a multiplied by 0, because we're plugging 0 in for t, squared, plus the initial velocity v naught times 0, which we plugged in for t, plus the unknown constant c2. And again, we've got stuff times 0 squared, so that is 0. And stuff times 0, anything times 0, that's also 0. So again, we're ending up with our unknown constant, c2, is equal to our initial position. So we can go back up here and erase c2 and replace it with initial position. So let's go ahead and write this equation down as well. Position, which is a function of time, it'll change as time changes, equals 1/2 acceleration times squared, plus the initial velocity multiplied by time, plus the initial position. And again, we can sort of see that this equation makes sense. Where you are depends on where you started, how fast you were going when you were starting, multiplied by how long you've been moving, and then because your velocity isn't staying constant, it'll also depend on, okay, how much have you been accelerating? What's been the change in your velocity? It has a stronger dependence on time, so t is squared, and then we've got the 1/2, which came in because we did the integral. So we got two equations that we can use whenever we're modeling acceleration as constant. We can keep going. Say we know that acceleration is constant and we have some information about our initial position and our initial velocity and what the acceleration is, but we don't have any information about how long it's been, so we don't know t. We can solve for t and get an equation that doesn't have time in it anymore. So we're going to solve for t in one equation and plug it into the other. And we're going to do this because then we'll get an equation that doesn't have time in it. So we can use it for situations where we know the acceleration is constant and we know stuff about the initial position and the initial velocity, but we don't actually know anything about how long it's been, what the time is. So let's solve for time in this equation, because it looks a little bit simpler. This one has time in two places and one of them squared. So we have velocity equals acceleration times time plus the initial velocity. We'll subtract the initial velocity from both sides, get v minus v naught equals at, and then we're multiplying times by acceleration, so we'll want to divide it, so those two will cancel, but of course we must divide both sides by acceleration. And here we have an expression for time, and now we can plug that into our other equation right here. So position equals 1/2 acceleration multiplied by time squared, so we're going to have to put in everything that's equal to time, v minus v naught over a, square the whole thing, taking care of this term, on to the next term, v naught, plug in everything that time is equal to. So that's time, this was time squared, and then our third term, which is just initial position. All right, so let's go ahead and simplify this. First, I'm going to subtract off initial position from both sides. I'll get x minus x naught on this side. Initial positions will cancel on this side, and then we'll go through and see what we can do. We got a 1/2. We have acceleration. I'm going to square the top and the bottom of this fraction separately. So v minus v naught squared over a squared, because then I see, I have 1 acceleration up here, 2 down here, and we'll cancel one of those. And then here I've got, I guess we'll distribute this v naught inside. So I'll have v naught times velocity minus v naught times negative v naught, so that'll be negative v naught squared over acceleration, and the initial position I canceled, I moved it over here. Okay, so then what do I see what to do next? Well, I think let's go ahead and solve for velocity. And I see that every term over here is divided by acceleration, so let's just multiply the whole equation over here by a, and then of course we must do the same thing on the other side of the equation. So I'll get a times the difference in position, our position minus our initial position, and then over here I'll distribute the a to this first term. We're multiplying and dividing by a, so those will cancel. So this will become 1/2 v naught, or sorry, v minus v naught squared. Distribute a, multiply it by the second term, so it'll be multiplying a and dividing by a, those will cancel. I'll be left with v naught times v minus v naught squared. Now I have run out of room, so I'm going to start up here, erase, so I've got a little more space. And I'm just going to write this whole thing up at the top again. Acceleration times change in position equals 1/2 v minus v naught quantity squared plus v naught times v minus v naught squared. All right, double check. Got everything looks the same, so I can go ahead and erase this. And I guess the next thing we should do is take care of this, square that guy. So acceleration times position minus initial position equals 1/2. And we'll square the first term, so we get v squared. And then we'll get the last term times the first term. We'll get 2 of those, so that'll be negative v naught v times 2. And then we will square the last term, so negative v naught. We have to square the negative, that'll become a positive, and v naught is squared. There we go. So we've taken care of that term. Now we got to do this term, plus v naught v minus v naught squared. Write everything again. Okay, actually maybe what I'll do is I'll distribute that 1/2 to all of these terms. So 1/2 times v naught squared is 1/2 v naught squared. 1/2 times negative v naught v2, well those 2's will cancel, I'll be left with v naught v. 1/2 times v naught squared, that'll be plus 1/2 v naught squared. Taking care of every term here, just double checking, yep, that's all of them. Then we write this term, plus v naught v minus v naught squared. Okay, now let's take a look. What do we got? We have some 2 v naught squareds. We have a minus v naught v and a plus v naught v. Those 2 will cancel. And then we're going to go ahead and combine these terms. We have, let's see, 1/2, that's positive, and a minus v naught squared, so that's implied minus 1, but let's go ahead and rewrite everything. A times quantity position minus initial position, x minus x naught, equals, and double check. All right, this is the only remaining term that has v in it, so we'll just write that. 1/2 v squared, and then let's write all of the coefficients to v naught squared. We've got a 1/2, and then we have minus 1. So together, those are going to be negative 1/2. So we're left with a times the quantity x minus x naught equals 1/2 v squared minus 1/2 v naught squared. Just erase that to make it a little bit clearer. And we're solving for this guy, for v naught. So then next, I see both of these terms on this side have got a 1/2. So I'm going to multiply this whole side of the equation by 2. Do the same over here. So I'll have 2a x minus x naught. Distribute this 2, I'll distribute it here. It'll cancel with this 1/2. I'll be left with a v squared. Take this 2, distribute it to this term. It'll cancel with the 1/2. I'll be left with negative v naught squared. And there I have an equation for the velocity that doesn't have time in it, which is what we were starting out here. We wanted to get rid of time, so we solved for time in one of the equations, and we plugged it into the second equation. So let's write this guy down. So first I'm going to add v naught squared to both sides of the equation. Those will cancel, and then I'll get v all by itself. So v squared, I'm going to remind myself it depends on time, it's a variable of time, equals v naught squared, the initial velocity, plus 2 times the acceleration times the change in position. Where we're at now minus where we started. All right, and we can keep going. Let us get an equation without a. So if we know that the acceleration is constant, but we don't actually know what number it is, we can manipulate these equations so we get an equation that doesn't have a in it, but it's still good for when we can model things with a constant acceleration type situation. So we're going to do the same thing we did previously with time. We're going to pick one of the equations, solve for a, and then plug that value of a into one of the other equations and see what we get. So let's solve this first equation for a. We have v equals acceleration times time plus the initial velocity. Subtract the initial velocity from both sides. We'll get v minus v naught equals a times time. Now we're solving for a, so we can plug it in to a second equation. So we're going to divide by t. Time will cancel on this side. We'll get the difference in velocity over time. That's equal to acceleration. Let's plug it in to this guy right here. So we'll have position is equal to 1/2 acceleration, but we're going to plug in what we know about acceleration. It's v minus v naught over t times t squared. So remember that guy's a right there. We solved for it over here and plugged it in. Plus initial velocity times time plus initial position. Okay, so then what happens? Well, I have t squared and I'm dividing by a t here. So that's t to the second power minus 1 because this is dividing by t to the 1. So one of those times will cancel. So we'll get position is equal to 1/2 velocity minus initial velocity times time plus initial velocity times time plus initial position. And then let's distribute out this 2. So it'll be 1/2 v minus 1/2 v naught, all of that times time, plus v naught times time, plus initial position. Now we distribute the t. So 1/2 velocity multiply time by this first term minus 1/2 initial velocity multiplied time by this second term plus initial velocity times time plus initial position. And then this is the only term that has v naught and t, or has v and t. These terms both have v naught and t, so we'll combine those two, and that's the only one that has initial position. Just rewrite that, and we'll combine these. We have negative 1/2 v naught times t plus 1 v naught t. So we got one of these minus 1/2. We're left with 1/2 v naught t here plus x naught. And then we can go ahead and rewrite this. Let's subtract x naught from both sides. We'll have 1/2, and I'm going to pull the 1/2 out of both of these. Well, maybe I'll do it in 2 steps. So now I can combine this. I see they both have a 1/2, they both have a t, and the only difference is the 2 velocities. So I can rewrite that as 1/2 v plus v naught times t. So all I've done is I pulled the 1/2, I pulled those out, and the t's, I pulled those back. So if you redistribute the 1/2 and the t, you'll re-get this. And the reason I read it like this actually has some physical intuition here. You have your change in position is equal to, well, this guy is the average velocity. The velocity you've got now plus the initial velocity. If your acceleration is constant, this guy is the average velocity multiplied by time. So let's write that equation down too. So that is the average velocity if, and this is very important, the acceleration is constant. It won't be the average velocity if the acceleration isn't constant. All right, hopefully what you found was something which looked like this. And you'll notice that this guy is really similar to this equation we've already found, except for this one has v naught, this one has our speed at the end at time t, this one is adding the term 1/2 AT squared, and this one's subtracting it. And if we think about that, that actually makes sense. Both of these are saying you can find where you are, your position now, if you look at where you started. And then here, you add your initial speed multiplied by how long you've been going, so that's a distance. We have to add in the effects of acceleration. We're going to have to add on to what we started with. This one's saying, okay, if we start at the other end, if we start at time t after the start, we're going to have to subtract off the effects of acceleration. So that's why these two are so similar, with just that sign change on the acceleration term and which velocity we're using here.